Yes, yeah, good. Thank you very much, Nicole. Thank you for inviting me to this very exciting series of seminars. I'm honored to present here. And yes, thank you for the introduction. Maybe a few words about myself. I initially from St. Petersburg, old Swedish city called once upon a time Nynäshamn. I did my PhD in Sweden, and I did my postdoctorals in Sweden and in Ohio, at Ohio State. And then for quite some time, to be exact, 15 years, I had been working in Canada, in Quebec. But then I got a little bit nostalgic, so I went back to Sweden, and now I'm fully at the Swedish University of Agricultural Sciences. And it's a little bit strange name. Many people note that, and fully agree with them. We don't really do so much of the agricultural science. It's forestry, and it's more like life sciences, as people nowadays you call the, like a little bit applied, but a lot of fundamental research with some applied functionality eventually. So Nicole was completely right that one of the main themes of my lab is the fire history reconstructions. Of course, we do tree ring, classical dendrochronology and stuff, but since we had so much work done on fire history, and since it connects so well to the idea of legacies of both climate and human impacts upon vegetation development or history of ecosystems, so I thought maybe I can just show you some hopefully sufficiently entertaining collection of slides, and just try to comment on them, and eventually we'll find it interesting and of some interest, of some value. So I will talk today about the possibilities of using tree rings to reconstruct fire history, and actually to deduce certain changes in the way people manage the forest, and in the way other factors, like, for example, climate, affect the dynamic of the forest dynamics and the history, the forest history. So there are a lot of people, not all of them mentioned here as authors, of course. A lot of students and my colleagues, they contributed, so I just grabbed this title page, which broadly corresponds to what I'm going to talk about. But before I go into fire history, I just want to say a few words about tree rings, because I'm supposed to give you a broad introduction to the idea of using tree rings for some purpose, right? So we think of the tree rings as something which we can in one way or another. And typically when we, again, think of tree rings, we think of the northern hemisphere. Okay, a little bit in southern hemisphere, but largely a northern hemisphere in the temperate climatic zone. And why we do so? Because in these regions we have tree ring as an annual phenomenon. So a tree ring in 90% of cases correspond to a single year, a single calendar year. And this is very good, because it gives us very strong control of where exactly a certain ring has formed. We can use multiple methods to date rings, from artifacts, from just dead wood in the forest, from live tree in the forest, by making basically a connection between a specific ring and a calendar year. That's something we call dating. We can do it on the wood, which goes very long back in time, and we can actually date certain events, certain historical events, just by looking at mortality dates, or sometimes regeneration dates, again by dating the actual tree rings, annual tree rings, against certain master chronologies, certain chronologies. Well, they have, we can, for example, do a correlation. So one of the beauty of a tree ring research is in the fact that we have this very, very well dated, like dated at the annual scale. Why I emphasize this? Because on multiple occasions, people contrast other reconstruction methods against tree rings and discuss advantages and disadvantages of these techniques. Well, a clear disadvantage of this technique is that we're heavily dependent on the presence of the old material. And this old material simply may not be around, right? People have been collecting wood for hundreds of years. All kinds of things happen in the forest, for example, fires which destroyed, basically burned out the wood, and we don't have the very old wood just laying on the forest floor just like that. We'll have all kind of land use patterns which actively removed wood from the forest. So it's very difficult to go back in time in majority of sites, in majority of forests, simply because forests have their history, and this history basically made it very difficult to get things which are old. It's not impossible, but it makes things way more difficult compared to other reconstruction techniques. If you think of, for example, paleo records, it's much easier to find a lake which have sufficiently interesting and sufficiently long sediment record, which sometimes extends, quite often actually, extends over thousands of years, and sometimes over the whole Holocene, last 12,000 years. So this is a very strong competitor with the dendrochronology for the position of the best reconstruction method. Of course, it's not such a competition, but to give you just an idea that the multiple ways you can reconstruct things using different proxies, different natural archives, but all of them, they have some positive and negative sides, so advantages and disadvantages. In this case, in case of paleo record, we don't really have capacity to go to the annual resolution, right? Even with modern dating, AMS dating, the resolution of the method is approximately plus minus 30, 40, 50 years. So it's not really annual. And sometimes a lot of critical things, for example, variability in climate, or even variability in the way people operate, do things on the land, it happens at much shorter intervals. So resolution is a very fundamental thing. That's one thing I want to say. The second thing, I wanted to say that when we measure tree rings, we can measure it in different ways. The most easy way and the most cheap way, I mean, absolutely the cheapest way you can even think of, which is very good, is just measuring tree ring width, right? The width of the ring which you recovered using a coring device or using a chainsaw, for example. But it's not the only thing you can measure in tree rings. You can measure, for example, density. You can measure isotopes. You can measure parts of the ring. For example, you may measure a part which is produced towards the end of the season. We call it late wood. We can measure part of the ring which produced at the beginning of the growing season. We call it early wood. We can measure width. We can measure density of these parts. And of course, we can measure such things as isotopes and even chemistry nowadays. And sometimes it can be done with incredible resolution. In this case, spatial resolution. So we can measure, for example, something which corresponds to concentration of certain elements with, I think, 20 microns resolution, which is very great. So all these kind of measuring techniques, they are based on one major assumption, which is very nice to know. This is actually one of the principles which drive the whole dendrochronology. And this is exactly the principle which I put on the slide, the principle of limiting factors. And this principle says that you really want, no, it doesn't say so, but the outcome of this principle is that if you want to measure something, it kind of assumes that this parameter, this type of measurement, represent reaction of a tree to certain natural variability, and this variability exercises certain limiting effect on the growth. For example, we'll have the tree growing on a rocky outcrop, so we can assume that growth is heavily limited, strongly constrained by precipitation. So we can expect that ring width, or maybe even density, or maybe even isotope concentration is constrained by this. So it has it's impacted by this variability in precipitation. So if we will study the response, if we maybe even use the tree ring data from this tree to do some reconstruction, so we can expect this signal being present in the past, and this signal being simply available just because tree is constrained by this specific factor. So if its tree is not constrained by the factor we are interested in, there's very little you can do to actually recover this factor and do some analysis. So we always look for trees which are constrained by the factors which we would like to work with, understand the response of the trees to this one group of factors. But today, I'm not gonna talk about this. This is another slide, very general slide, which just here to illustrate variability of the whole thing. Like you have variability, which is very easy to see in the ring width, but you also have variability in density, which can be approximated by just the color. And it has also a lot of variability which we don't see. And this is, for example, variability in chemical composition, isotopic composition. So all these potentially carries different signals of past environment, kind of natural archive, something which we eventually may want to reconstruct to extend our chronologies, which we collect just now with instrumental, like measuring environment, right? But long time in the past, we didn't have this chance, so we have to rely on trees which eventually recorded something. Of course, you may wonder, well, how do we extract this? This is a major challenge because we oftentimes have a tree ring, which is not oftentimes, literally every single time. We have a tree rings which are integral of a lot of things at the same time. So one really difficult task, which we always face, is to actually separate this impact, separate different partition, different influences, in the hope that you can maximize the one which you are interested in and then work with that one. So this is one of the kind of main challenges which we face as people working with tree rings. This is just another example of very nice variability, which you can immediately gives you a, like, kind of offers you some thinking. What could be the reason behind this changes in this case in density? You can also know that there are some things which don't really correlate so well. Like the width of this tree of this ring is rather similar to the width of the next one, but the amount of darkness, the density of late woods, which is this part produced towards the end of the season, is very different, which tells you that probably something different happened, something which made these 2 years very contrasting, very different from each other. Okay, so, but now you learned about this. That was a little bit of the theory or kind of general introduction. So now let's jump into the fire. And before I actually jump into the fire, I strongly suggest that if you hear that I'm breaking, my signal is not good, please let me know, right? Because I know that somehow towards the presentation, the quality may decline, right? And I will be maybe telling you the most interesting part of the story, and you will be just hearing some totally impossible to comprehend noise, right? So let me know. So forest fires. Forest fires is very fundamental disturbance factor, which you can say, and that would be not an exaggeration, the factor which drives dynamic of the boreal biome. Of course, you should know what is a boreal biome. It's a biome where you have coniferous trees being the dominant part of vegetation. This is a boreal biome. There's also importance of this, you can also mention importance of this factor, forest fires, in other biomes, in places, very exotic ones like fynbos in South Africa or Mediterranean ecosystem, or in the temperate zone. This would be correct to say that they are also very important there, but I would like to focus today at the boreal biome because most of the data we have been working in Alnarp with came from this region. So fires are very important. And just based on my work in different parts of this boreal biome, I would like to touch upon two histories, two stories, one from American Northwest and one from Scandinavia. And at this point, I just need to check I'm not really going too slow. Oh, I'm going too slow, right? Nicole, how much time do I have?
You have between 30 and 45 minutes, so.
Okay, that's good.
As long as you like.
You have to show me some fingers telling me how many minutes are left, right? Because I can talk for quite some time, and I know people get tired and they say, Igor, I mean, you're talking like way too broad and like really undirectional. Let me, okay?
I can send you
Yes.
a message in the chat when it's close to time to wrap up.
That's right. That's right. And I hope Mia can also help me if I go totally like without much of the clear focus. I believe it will be also helpful if people say, hey, stop it, just stop it. Okay, so 2 stories, and again, they are not really fully published. We'll have lots of publication, of course, but it's still work in progress, even if we say that there's something established or not established. Okay, so I'm going to talk about data collected with the help of something we call fire scars. And what is a fire scar? Just imagine a tree, and tree has a cambium. Cambium is basically a layer of cells which allow a tree to grow, right? Around the tree, there's a cells which grow actually 2 directions, and it makes tree larger. And then this cambium dies, tree stops growing, or sometimes it dies, typically it dies. But there are some trees, for example, pines, and some other trees, also oaks, for example, which are very well adapted to partial cambium mortality. If part of the cambium suddenly dies, sometimes they die just because of some internal dynamic within the tree. But oftentimes, like with pines in natural forests, they die because of some damage. And the heat during the fire can induce such damage. And then if heat is not very strong, or if the heat doesn't really cover the whole tree, if fire doesn't go into the crown, then many trees, especially pines, actually survive. And then they produce something which we call a fire scar. This is on the left, you see a tree with multiple fire scars. I don't know if you see my cursor, but I'm pointing at the one scar and then another one, and then even more. Then so I see 4, 1, 2, 3, 4, maybe even 5 scars in a single tree. So if fires are very not very severe, trees get damaged every single time fire passes by, and the tree functions as kind of recorder. They can actually record the history of this disturbance event. So when they eventually die, you can come to this place, hopefully with your hardworking student, like we'll have on the right picture here, it's my student Nina, and use a chainsaw and actually take a cross-section. Sometimes you're not allowed to take the whole stump, the whole snag. So we take something called wedge, like part of the circumference. And then you can actually look for these fire scars. So this is how it looks. So on the left, you see how it looks when you polished the whole thing. So it's a cross-section. And then you see fire scars, which look at kind of structures, kind of which follow circumference of the tree, right? And sometimes they're very visible from outside. If I go back, so these are the scars which are very visible, right? You can see this kind of overhealing. The tree tries to overheal the whole thing. But sometimes they're not so well visible. Like, for example, in the one which I highlighted by this little bit palish square, and then another square just below, right? So it's very important you actually take cross-section, because here you see a lot of things which are otherwise very difficult to see just by looking, just standing at the tree. So you can, again, make use of your very hardworking student and tell him or her to polish it very well. And if he's listening to you and polishing is done, you can actually look at the way they look, and you can see that they're actually perfectly datable and perfectly easy to see. Like this, on the upper image, you see the scar, and you see that the tree growth, which was very nice. So the tree growth from the right to the left, and then at a certain point, sky hit the tree, and then immediately you saw the kind of disturbance of this growth, and growth reaction tree didn't produce so much wood in the years that followed. And then at the lower image to the right, you see where this actually sits. So we go further into this section. You know, this is actually a place we call scar face. It's a place where cambium survived, actually, because before that, cambium died, it was too hot. But further into the tree, it survived. And then if you just proceed into the parts where cambium survived, you can actually see how scar is positioned itself. It sits right in between, in this particular case, not always, right? Just this particular case, it sits in between early wood. This is part of the ring which is light, and late wood, which is part of the ring which is dark. And we wonder why it's called late wood. Well, because it's produced late in the season. And the second question, fully legitimate question, why it's so dark, is because the cell wall thickness is just larger. You have thicker cell walls. You have more lignin in these cell walls. So it appears as a darker structure, right? So in this particular case, you see that fire happened right when trees start producing late wood. And if you know phenology of this tree, you know that in this region, this tree species used to produce late wood starting from this date, from this week, for example. So suddenly your dating becomes not only annual, but also seasonal, even like I would say weekly, because you can actually identify part of the growing season or fire season when the whole thing happened, right? So this is totally fantastic, a possibility, because you can do this on old deadwood and then extend your seasonal, actually not even annual, but seasonal reconstructions for decades and centuries back in time. Okay, so this is the way it looks. Again, this beautiful picture. This is a close-up. You have multiple fire scars. This is red pine from North America, a species which is very similar to Scots pine in Europe, very well adapted to fires and have beautiful ability to survive fires, capacity or feature which we call serotiny. Serotiny, it's adaptation to fire. So you can come with a chainsaw and take a cut, not kill the whole tree, of course, but take a veg and then date these features which I just showed you right here. Okay, so this is the way fire comes. Of course, these scars, they were produced prior to this fire, right? So first, when tree comes, the tree doesn't really produce scar immediately, right? If it survives, it just first cambium gets killed, then at a certain point, bark drops off, and then you see the first scar. And then the second scar, if second fire comes, it produces the second scar on this spot. Okay, again, a beautiful scar. Now the tree grows towards the bottom, right? And you again see that there's a possibility to see the seasonal dating. So in this case, it was not immediately at the border between late wood and early wood, but somewhat towards the end of late wood still, early wood, sorry. And now you can also think, oh man, it seems like you have ability to date a lot of interesting structures in the forest. And you're completely right. Like this structure. Now, this is my favorite slide, so I allow myself to actually ask you, my dear listeners, what do you actually see on this image? So if somebody can just raise your hand or just shout out in the towards us, so we can have some short but hopefully meaningful discussion, please. Okay, Mia, I'm quite certain you are so into this very bizarre structure, so I think you should be the first.
Oh, but I'm an artist. I guess I could see the cross section into the wood to the center, I believe.
This is true, okay. But what was the source of this strange structure, right? It's something which clearly tree didn't produce by itself, right? You probably can.
It's been sampled or cut.
That's correct. Do you see something more?
Well, it's grown over that cut. So this was done a long time ago.
Fantastic. Do you see even more?
Like humans here?
Yes, that's right. Clearly, well, cuts typically done by humans in the forest. That's right. But there's something which I just mentioned, which I hope you see also on this picture.
Dilianas?
You can see lines from fire showing as the thing grows back. And you can also see that the initial cut at the top is not even. So I don't know what implement made these cuts, but it may not be a modern implement.
That's correct. This is excellent. I really enjoy your very careful and very insightful comments, because this is exactly what we see here. First, we see a cut, and it clearly has been done with the axe. And I would even argue that the guy who came and did the cut has been very proficient in using a very, not proficient, but very professional in the way he used his tool. Because if you look here, you see that it took him literally 2 cuts to get to this center, right? That was the one, and that was the second one, right? I hope you see my cursor, right? Or you don't? Do you see my cursor or not?
Yeah, we can see it.
Okay, that's good, because sometimes, yeah, okay, very good. And then, for some reason, he left, right? He did this cut, he left. We don't know why. We can speculate, but clearly his intention was fine thing, right? Then he left, tree didn't die, survive. And then the fire came and produced this structure, right? It was a single fire which produced a fire scar. And fire scar happened after the tree was hit by the fire. And then the last event in the history of this tree, yeah, now I will probably ask one more question. So what was the last event in the history of this tree which we can eventually date using tree rings?
The tree's death. It has no bark.
Perfect. Excellent. Excellent. That's exactly what we're doing. Perfect. That's right. So we can actually, using tree rings, date a whole lot of things here. Of course, we can date the time the tree starts growing, right? If the center of the tree, the pith, is still preserved, we can date the time human came and did the cut and left. We can also date the time of fire, and we can also date the mortality event. Some of them are very relevant for reconstruction or understanding the history, human history, some for understanding dynamics in the forest. I don't have the dates right now. We dated this, but unfortunately I was rushing so fast and I unfortunately didn't have time to really find the slide with actual dates, but we'll have it somewhere. So, but my point is that it's very interesting to really look at different legacies or different events which are kind of impregnated or present in the wood, in the dead wood, and really try to build the chronologies of, for example, use of the forest by people just walking around there doing something, or by fire history, or by making chronology of fire history. Okay, so this is the way we take samples. We typically don't cut the whole tree. We take something called veg, so tree stays on the spot, and surprisingly, it doesn't really make tree fall or die. Pines are perfectly fine with this type of sampling, so you may get quite a lot of data and still have a lot of trees standing. So that's very good. So back to American Midwest, we have several periods. We have pre-European conditions, we have colonization and commercial forest use, and then we'll have something we call fire suppression era, when people realized it makes not so much sense to like burn the forest, and it makes a lot of sense to actually preserve forest because it's a source of revenue. Timber can be sold, and that would be way better than burning it or doing something else. So, and then we made a reconstruction. It was part of my postdoctoral work at Ohio State, though it was in Ohio State. I was based in Ohio State, but I did it in a place called Upper Peninsula of Michigan, which is a beautiful place, just on the border between Canada and the US, but you can listen to Canadian radio, which I was actually quite impressed with. I was driving there, and then it was quite a long drive from Ohio. I was at Worcester, Ohio, and once I picked up the radio, and it was like kind of meaningful radio, a lot of interesting stuff, and they treated you like an adult, right? I was like, they have quite cool radio. I thought, and then on the way back from IHOPE, I also found it, and I was listening, and I was really enjoying. And then I came back to Worcester, and I talked to my boss, Charles Gerbrel, a professor there, and I said, Charles, it was actually quite cool radio in IHOPE, and I started telling him what I was listening to, and he laughed. Said, "Igor, it's a Canadian radio." So sorry guys if I made you a little bit upset with the quality of American radio, but that was kind of funny experience. I realized we're very close to Canada. I did this, and I created a very large network of sites where I reconstructed fire histories. And most of the times it went to 300 years back, sometimes more, sometimes up to 500, but most of it was a little bit more than 300 years back. We had a part which is called wilderness area. This is this section, and this section I got trouble with because I sampled way too more than I promised, and actually I ended up receiving a letter saying, I was really stressed actually by this letter that says United States of America against Igor Drobyshev. So they took me to the court because I sampled way too much. But here I sampled fine. They were not very unhappy, so it was good. So, and we did these reconstructions, and by the fires class, we created the chronology for each of these points, and we identified years which were large fire years, the years where majority of this landscape has burned. And this is a beautiful landscape. We have something called mixed pine forest. We have red pine, we have white pine, and we also have jack pine, Pinus banksiana. They all live together. They kind of adapted to fires of mixed severity, sometimes severe, but generally not very severe. So you have very beautiful, truly beautiful landscape with like open forest, like relatively open forest, and very easy to walk to, and like really pleasure to stay there and do the research. So this is an example of large fire year. You see, this is like what that year. We didn't have wood from that year. They are white ones, and we'll have fires. Oh, sorry, we'll have sites which majority of landscape has been burning, like it was a huge fire problem. So we can actually look at the frequency of these large fires and see if there is a tendency of these years to get like for these years to be more frequent or less frequent over the time. So this is the reconstruction we got. We got the first large fire in 1752 and the last one in 1976. And I have to tell you that all this, like you see this periodization, pre-European conditions, we'll have colonization, and we'll have a fire suppression era. Each of these periods has their own large fires, and apparently you may conclude that in the colonization era, these years, you have more of these years, right? And then you may conclude that the reason for this is because you have actually humans in the landscape which create a lot of ignitions and then fire spread. This is one of the main topics of discussion when people reconstruct fire activity in the forest, because you have humans and you also have natural variability in climate, which can make certain years very fire prone. So even landscapes which otherwise are not really prone to fires can ignite very easily. And situations where you can hardly imagine any serious fire, for example, like wetlands, they can dry out and they create a perfect fuel bed for all fires to spread across. So this is very difficult situations for any fire control, literally impossible. And then they create perfect conditions for very large fires and eventually large fires. So the question is if this is really product of human activity or product of climate variability. There's a plenty of analysis which you can do. I'm not going to go into this detail. I can just tell you that overall, it's still a little bit debated, but overall understanding of this is that we have a strong climate signal in the periods where humans have been already very active in the landscape. They have been cutting forests, they have been creating some ignitions, sometimes very occasional and unintentional ignitions. They were, for example, cooking something or just walking in the forest, or having picnic, or just warming themselves up. As soon as you have humans, you always have additional sorts of ignitions. And oftentimes people say that, oh, this source of ignitions they're always the one which controls how much area burned. And this is not exactly true, because amount of area burned is primarily controlled by the ability of the fire to spread across the landscape. And it is simply constrained by the humidity of the air, wind, and the temperature, right? So if you have a lot of ignitions, you will take like all your students you can get and throw them into the forest with the instructions to ignite as much as they can, but it will be a rainy day. Nothing will happen, right? So you may have plenty of ignitions, which will probably cover an area of few square meters, but will never result into large fire. Though, if you have very strong fire-prone conditions, you don't even have students in the forest with this very vicious, or I would say very bad and this terroristic like instructions, right? You can just have a very natural ignition from lightning strike, a single one that will be sufficient to ignite very large fire, which will be very difficult to control. So oftentimes you hear people saying, oh, 99% of forest fires are caused by humans. This is true, but these are not this amount of fires which we can easily convert into the area burned, right? We don't need to have a lot of ignitions to have a lot of area burned, because it's not the ignitions but the conditions of fuels which define the fire spread possibilities. So this is a very important thing to understand and to keep in mind. So don't let you fool by statistics that say that indeed 99% of the fires are caused by humans, yeah, but they are not relevant. They're simply not relevant. It's really the amount of and severity of the fire weather which controls what will happen with these ignitions. And at a certain point, it doesn't matter if it's ignition caused by human or it's natural ignition, which are always there, which create this very huge fire, which will cause like a lot of disturbance, like we had in Canada, for example, this year. Okay, and Nicole, do I have still some time for my broadcast, or it's like getting really tough?
You have about 7 minutes left.
7 minutes,
if you want. Yeah.
Like, okay, now we're gonna squeeze as never before. So. Yeah, Scandinavia. Scandinavia is a little bit different story, because in Scandinavia we have natural fire regime prior to 1600s. And then we'll have slash and burn agriculture, something which was largely missing in America. At least we don't have much information about that, but overall we can say it's probably have been missing. And slash and burn is a very common technique in literally all boreal zone, especially for the frontier population of people. They come and then they need some food, right? So you need to get some agriculture going, and then they cut the forest, they burn the site, and they use it for agricultural produce. And of course, this is very unfortunate, highly inefficient way of doing things, because these are the forest soils. They're typically podzol. They're highly nutrient, no, not highly, but very nutrient poor soils. So there's absolutely no reason to expect you will have some decent harvest after 3 or 4 years. Sometimes even after 2 or 3 years, they got abandoned and they were moved and they had to do something more. That time, manure was still not really a part of the whole agricultural system, so overall productivity was really low, like really not even low, just truly unfortunate productivity. So that was around 1600s and 1700s, but then since 1800s in Scandinavia, we have this idea that actually we have quite efficient agriculture. We have enough of the land which can be used in a much better way. And then timber becomes a commodity, becomes something which you really want to sell. And you don't want to have fire in the forest because it destroys your commodity, right? You have to be insane to really allow fire and destroy something which you can sell for quite a lot of money. So little by little, fire suppression ideas start to being introduced. And of course, sometimes, not sometimes, but initially, ideas were extremely, like they were enforced, but of course there was a problem with enforcement. They were not always like really truly enforced. And sometimes, and of course it was very difficult. The technology was very minimal and it was more like a passive fire suppression. But little by little, towards mid-1900s, we had quite good suppression. And now we have very perfect fire suppression. I can tell you that nowadays, even if media tells you that, oh, we had a large fire in 2018 or large fire in 2014 in Sweden, it's still approximately 100 or 1,000 times, between 1,000 and 100 times less than has been burning in the 1600s or in the 1500s. So we still live literally in a fire-free world. in this part of the world. Okay, and just to illustrate how things worked, everything has been done on the fire, on the triggering data. So my colleagues went to this part of Sweden, it's northern Sweden, right here, and they looked at the landscape, which was, what is that, approximately 40 by 20 square kilometers, and they really spread a lot of sites in this landscape. There's really massive sampling effort put into this, and they reconstructed fire history in this landscape. And what they found is that in this period, like early 1500s, first half of 1500s, we'll have relatively few fires, but they were very large. They really, most of them actually extended beyond the area covered by the study area. So we don't even know what was the actual size of these fires, right? A lot of them, they just went outside. That was in first half of 1500s. Now we see what happens in 1800s. It's totally different story. Fires were extremely tiny. Almost all of them, they are constrained or contained within the landscape which they studied, and their frequency is very high. This is a perfect signature of slash and burn agriculture. People are burning and burning, and they were like cultivating things, and that was quite successful. And now everything stops. And after that, towards like maybe second half of 1800s, everything simply stopped. And again, this is accumulation curve of amount of fires. You see accumulation has a quite major jump at the 1817, 1800s, and then it goes into plateau more or less at the turn of the century, at the beginning of 1900. So this is a chronology. Each line is a site, each dot is a fire on this side. And what you see is that there's plenty of fires, different, sometimes fires, they were really across the whole sites, the whole area. Sometimes they were not, just a single, like smaller fires. But then towards already at the late, from 1700s, there were basically nothing, just fire activity ceased to exist. And again, what was the reason? Well, it's a fire suppression. But the thing is, and then we'll have, okay, I can maybe finish with this one. Of course, if you have a data from a single site, it's very difficult to make a lot of strong statements, right? You need to have a network. It's probably one of the key words which everybody wants to make a point with or rely on in their studies, to have a network of sites. And this is a network. It's actually a smaller part of the network which we have, which is now actually being analyzed. I probably tonight after this presentation, after this seminar, I will take a look at what my student did actually write on this data. But this is the sites when we dated the onset of fire suppression, and we wanted to know if there's any correlates, if there's anything, any pattern which we can see here. And then we did this very primitive analysis. It has been done actually many years ago. Now we're going to do something more advanced. So you see this all sites, they show kind of plateau. You don't have really much of fires after, like sometimes late 1800s, sometimes late 1700s, but it's like kind of no fires ultimately. So we made this very simple thing. We said, okay, let's do it timing of fire suppression. On the horizontal axis, we'll have timing of fire suppression in years, right? It's calendar years. And then on the vertical axis, we'll have latitude, right? We have a beautiful country, Sweden. So it's a very long country. So it has a very lovely gradient in climate, in the bioclimatic, in the bioclimatological or like biomes, we can say. So we have emerald forest in the south, we have taiga up in the north, and of course we have Stockholm, the capital, from where enforcement actually initiated, like originated, right? So it was kind of interesting to see if we have anything. So we thought, okay, latitude may be a proxy of all this. So we just made this simple graph where we'll have onset of fire suppression on the vertical axis, on the horizontal axis, and then we'll have latitude on the vertical axis, right? So what we see is that there's actually a certain pattern which tells us that fire suppression started way earlier in the south than in the north. and the difference could be up to 200 years. So, and this is Stockholm, right around 60 degrees latitude. So you may wonder if there's any pattern below Stockholm. Actually, there's hardly any pattern below 60 degrees latitude, right? The pattern starts appearing if you go up north, more or less. So is it purely human pattern, or there's some climate which is baked into this analysis? Our hypothesis is that there are actually both, but since I probably don't have even 3 minutes to talk about this, right? So I will probably stop here, and let's see if I have one more slide. So yes, so just to sum up, and again, I should apologize for this highly incoherent presentation, probably with some amount of politically incorrect statements. My apologies, but still, I think it's important to conclude, make some kind of structured take-home attempt for a take-home message. So here it comes. So we'll have networks which are very fundamental, whatever you do, whatever you try to achieve in terms of understanding the history, because oftentimes tree rings, it's about understanding the history. So you have to collect a lot of data. Ideally, the data which stretches across multiple gradients. So you can actually see how your process which you study, how does it behave in time, but also in space. Spatial reconstructions are very fundamental. I didn't talk about this. Well, actually I did. So you can have a frequency data, amount of fire at a point within a certain nature reserve, within a certain area. But way more fundamental is actually amount of area burned, which you can actually reconstruct and use it as another proxy of human or climate impact on past fires. So always try to get a better proxy, even if you are, even if it may be way more difficult, way more pricey, it still gives you way more appetizing starting point, or way more starting point to actually talk about these things. And then, of course, any dynamic is of interest because it tells you that something happened. So I don't know what I'm supposed to say here, but it's important that you actually try to interpret all changes which you observe, right? You don't really discriminate, differentiate, or even if your explanation may not be very complete or maybe very speculative, it's perfectly fine. This is typically very hardcore data sets. They are actual fires which you reconstruct. They are not some speculations, but then based on this hardcore data, I think you may eventually allow yourself for some kind of a little bit more speculative approach. To have more, yes, of course. And of course, if you study things which are inherently complex, it's very important that you make an effort. You should make a decent effort, diligent and decent effort to separate the signals. Even if you are by nature of your project interested maybe in humans or maybe in climate, it's still important because by separating the signals, you enhance the pattern coming from a specific factor. Maybe that's a factor of your interest, and then you can actually be on a much better ground to actually discuss the dynamic of that very factor. But initially, you have to separate. You can't really throw things into the same analysis, assuming that this is the factor the dynamic which you see is a product of the factor you are interested in. Oftentimes, it's really a mixture. And oftentimes, the patterns which we recover in the climate and in the human behavior, in the human land use history, they are patterns which actually work in concert. Like you have periods where you have more fire-prone weather, and at the same time, you have land use policies which actually push people towards using fire. So both climate and humans, they operate towards the same direction. Sometimes they operate in different directions. So things are very complex. So better proxies, large amount of data. This is something which is like these things, they are your friends. And with this analysis, eventually you can say something interesting and novel. Thank you very much.